Hello, today we are going to focus our lecture on design of laterally supported beams. In case of beam design, we will see design philosophy are of two types. One is for laterally supported beams, another is for laterally unsupported beams, right. So, today we will focus our lecture on laterally supported beams. In fact, in last lecture mostly we have discussed about the design steps for laterally supported beams. Basic difference between laterally supported beams and laterally unsupported beams is that the stress due to bending in compression will be different. In case of laterally supported beams, the stress sigma BC will become say 0.66 Fy, which will be equal to sigma Bt, where sigma Bc is the stress due to bending in compression and sigma Bt is the stress due to bending in tension. Whereas, in case of laterally unsupported beam, what will happen? This sigma Bc will not be 0.66 Fy, means it will have some other value, which we will discuss in next class, not today, that how to calculate. But today we will be focusing on the laterally supported beams, and then if we have time we will discuss about the buckling, wave buckling, because as we know we are going to use beam sections as say I section, channel section, T section like this. In those case wave thickness are much less than the flange width. Okay. So, thickness is less, so wave may have possibility to buckle. So, that buckling effect has also to be taken care while designing. So, those things also we will discuss after discussing this design of lateral supported beams. Now, last day as we have told that the different steps of design procedure for laterally supported beams, today we will just give an overview of the steps by 1 minute, then we will work out one example. And before that I like to introduce, means already introduction is there regarding shear stress. The average shear stress we know how to calculate. The shear stress, as we know, it is an important factor for designing of beam section. We know shear stress is going to vary along the depth of the cross section. Now, how it varies, little I have told last day, but I have not calculated how to calculate the shear stress exactly. That today I will give an insight of that, and then I will start the design procedures, right. And in fact, many things we know. So, I am trying to exclude those things about the shear stress, only which we have not discussed in the last class, that portion only I will discuss today. That means, only the calculation of shear stress for a particular section over the depth of cross section. So, as we know, the shear stress tau at any point on the cross section can be, say tau can be given as Vq by IV, where V is the shear force we know, I is the moment of inertia, and B is the width of the beam, and A is the area from which the shear stress is going to calculate. Suppose we are trying to find out, say this is neutral axis F, suppose we are trying to find out say shear stress at this point. So, area means the outer section of that portion, area into y bar, the CG distance, right. So, in this way we can find out the value V into A into y by IV. So, in this way we can calculate exact value. As we know, yesterday we have seen that the shear stress distribution along the depth of the cross section of a rectangular section will be like this parallelly, right. And in case of circular section also we will see it will act something like this, but the magnitude will be definitely will be different. And also in last class we have seen that the sudden increase of the magnitude of the shear stress at this level, right. This is not in the same level we have made, okay. So, at this level. So, as the width of the width of the section is decreasing at the wave. So, increasing the magnitude of shear stress, because this is VQ by IB, it is proportional, means inversely proportional to the width of the section. Similarly, if we have, say, suppose L type of section or angle section, this will, the shear stress distribution will be something like this. Now, how to calculate, that we will focus here. We know that tau max, what will be tau max? V into A into Y by I into B. This will be the tau max, say for rectangular section if we see, right. So, if we put the value, what will happen? Say V by I means 1 by 12 B D cube, and then B, and area means here when we are going to find out the maximum shear stress, that means area will be this portion, that means B into D by 2. So, B into D by 2, and Y means this will be acting at a center from here. So, this will become D by 4. So, into D by 4. Now, if we derive this expression, we will get finally something like this, that 3V by 2BD, where B is the width of the beam and D is the depth of the beam. So, that is how we can find out tau max value. Not only tau max value, at any point the shear stress can be find out through this, but problem will arise when we will consider the section as say T section or say I section like things. In that case, the calculation will be little complicated. So, in that case, if suppose we have I section, so what we have to do? We have to find out where it will be, and as we know, this will be acting as, means maximum tau max will be, if we see the diagram, sorry. So, maximum tau max will be here. So, we have to, in a similar way, we have to find out, right, where D is the total depth and small d is the this depth, right, and we know other terms B, T, etc. So, in this way we can find out tau max, right. So, these are the two things which I omitted in last class, which I wanted to introduce here, because we must know what is the maximum shear stress is developing at a particular section, and then accordingly we can find out the safety of the section against shear stress, right. And we know the closure provisions we have it has been given in the code at IS 800/1984. The clause has defined that the maximum shear stress in a member having all the distribution of shear stresses in conformity with the elastic behavior of the member in flexure shall not exceed the value given by this. That means maximum shear stress whatever we are calculating here, it should not exceed this value 0.45 Fy, where Fy is the yield stress, right. Fy is the yield stress of the steel. So, tau Vm, the maximum allowable shear stress, that will become 0.45 Fy, and maximum shear stress we can calculate, and accordingly we can check, right. Again, for unstiffened wave of I and channel section, the cross section of the wave can be taken as this, means area of the wave will be simply D into Tw, because D is this one, this is D, and Tw is this is thickness of the wave. So, area of the wave we can find out like this, right, where Tw is the thickness of the wave and D is the depth of beam, right. So, in this way we can find out the area of wave which will be required. Now, the shear stress developed can be find out, tau V is equal to V by D into Tw, right. Now, this recommendation has been done by the code, and this is valid only when the depth of the wave does not exceed 85 times the thickness. wave depth is d, if it is and wave thickness is t, then the ratio of wave depth to wave thickness should not should be less than 85 or should not exceed 85, right. So, this recommendation we can use if d by Tw is less than 85. For this case only we can use this recommendation, and it is also seen that the ratio does not exceed this 85. For all rolled steel sections, this ratio is less than 85. We have standard steel section, rolled steel section. So, here we have seen that all cases it does not exceed 85. So, for all rolled steel section we can use that formula, that is this condition, right. So, this condition we can use, but if for built up section if we use, then we have to go for calculation, right. So, when the ratio exceeds 85, the stiffener are necessary. In case of built up section, generally it exceeds the ratio 85. So, in that case what we need? We need the stiffener. For such stiffened wave, the allowable shear stress depends upon the spacing of the stiffener of the dimension of the panel. So, allowable shear stress will depend on the spacing of the stiffener of the panel. So, from that we have to find out, and all these things we will see case to case. And as we told that for all steel rolled section the ratio is not exceeding 85. So, we do not need to provide any stiffener. We do not need to provide any stiffener for this rolled section. Now, the design steps which we have discussed in last lecture, just I will give by 1 minute just to refresh again, so that you can work out the example. What are the design steps was given earlier? As you know, the first step was that calculate the load acting on the beam, right, and this design steps is for laterally supported beam, right. Laterally supported beam we are describing the design steps. For other case we will again make the other design steps, and in next step what we will do, the calculation of maximum bending moment and maximum shear force. So, we will calculate the maximum bending moment and maximum shear force for the beam with taking consideration of the loading and their boundary conditions. Accordingly, we can find out what is the maximum maximum bending moment and maximum shear force, because we have to check from the maximum bending moment point of view and maximum shear force point of view, so that the designed section can carry the expected load. Next step is we will try to find out a trial section, that we can find out from this equation, that is section modulus can be written as Z is equal to m by sigma BC or sigma BT, and here as the beam is laterally supported. So, sigma BC and sigma BT we know these are equal, and that is 0.66 Fy, right. So, we can find out maximum bending moment and the sigma BC or sigma BT, then we can find out what is the modulus, section modulus is required. Z is nothing but the section modulus, and m is the maximum bending moment, and sigma BC is allowable bending stress in compression or in tension. So, in this way we can find out. Next step what we will do, we will go for check for shear, right. Now, from IS handbook a suitable section we can find out having section modulus equal to or more than calculated modulus of section. ISLB or ISMB sections are generally preferred. In practical cases we will see mostly we use ISMB or ISLB section, right. And so, we will try to find out a suitable section where section modulus will be little higher than the required one, right. If it is little higher than the required one, what will happen? Then the developed stress in compression and in tension will be little less than the allowable one. That means it will be in shape. Next step what we will do, that beam will has to be checked against shear. The calculated average shear stress should not exceed the value 0.4 Fy, where the average shear stress is given by P by dt, P or V we can write V by dt, where V is the shear force, right. So, from this we can find out the average shear stress, which is should not exceed, means it should not greater than 0.4 Fy, right. So, that we have to check, and next check is the deflection check. We have to see what are the deflection is coming due to that particular loading condition and that particular boundary condition. So, what is the maximum deflection for that case, we will check, we will calculate, and then we will check with the Codal provision. In Codal provision, it is given the maximum allowable deflection is span by 325, right. So, that we will check. So, that is what we have done, that after the beam is checked for shear, it is checked for deflection. The calculate value of deflection should not exceed span by 325, right. Now, calculate value we can find out, say two cases we have cited here, that one is say if it is uniformly distributed on a simply supported beam, means if it is like this, say this is W and say this is L and EI, then we can find out that maximum deflection is 5 by 384 WL to the power 4 by EI. Okay. So, in this way we can find out the maximum deflection, and similarly for concentrated loads on simply supported beam, what will happen? Concentrated load if we use on the simply supported beam at the mid span, then the maximum deflection will come WL cube by 48 EI, where W is the concentrated load. Here remember this small w is the uniformly distributed load, that means load per meter run or per unit length, right. So, in this way we can find out the delta, means deflection which is coming, and we know what is the maximum deflection we allow as per the Codal provision. So, that we have to check. If the calculated deflection or developed deflection is greater than the allowable deflection specified by the code, then we have to redesign the section, otherwise we can say that this is safe against deflection point of view. Next, we will see that it should not be failed against crippling. In last day we have shown how crippling affects, right. So, the beam is checked for crippling. The bearing stress calculated should not exceed the value of 0.75 Fy. So, we know crippling where it is happened, basically when the load is acting as a concentrated load at a particular section, then on that section, on that portion, the crippling effect may happen, and at the support, where the support, suppose a pin support is there, where the concentrated reaction will develop, there also this crippling effect may happen. So, we have to check there whether this is exceeding the bearing stress or not. So, sigma p calculated, that will be P by B plus 2H2 root 3 into T, right, for concentrated load, and for reactions this will be sigma p cal is equal to P by B plus H2 root 3 into T. So, in this way we can find out the calculated bearing stress, and we have to see whether it is exceeding this value or not, the Codal provisions where it is given that 0.75 Fy. Okay. If it is below the exceeding means limiting value, then fine, otherwise you have to go for some other sections. Now, the example we will sort out. Last day we have discussed, means we have given the example for making at your home, right. I hope most of you have already done this problem. So, now I will demonstrate the same thing, and you can check with your workout example, and you see whether it is matching or not, right. So, last day what we told, that a simply supported steel joist with a 5 meter effective length, 5 meter effective length, right, and carrying a uniformly distributed load of 50 kilonewton meter, 50 kilonewton per meter, right, including the self weight. Right. The beam is supported laterally throughout. So, it is supported laterally throughout. Now, select a suitable section and check its safety. So, supported laterally throughout means sigma BC will become 0.66 Fy, or sigma BT also will become same. This is always, this will be, and sigma BC will be this one, right. So, in this way, means with this consideration we have to design. So, first step what we will do, we will find out that what is the load, total load coming into the beam, and as it is told that total load is 50 kilonewton per meter length including self weight. So, we do not need to include again self weight. So, we can make UDL load as 50 kilonewton per meter length as a load to calculate the design sections. Now, with this we can find out the maximum bending moment. Maximum bending moment for simply supported beam, what will become? This will become M is equal to WL square by 8. We know maximum bending moment becomes WL square by 8. So, here W is 50 kilonewton per meter and length is 5. So, after calculating this we will get 156.25 kilonewton meter, 156.25 kilonewton meter, or 156.25 into 10 to the 6 Newton millimeter. So, maximum bending moment against which we have to design the section is now known. Next, maximum shear force. We know for a simply supported beam, maximum shear force will develop at the end, at the support. So, that will become WL by 2, right. So, W is this, L is this. So, we can find out maximum shear force WL by 2, that is coming 125 kilonewton. Now, in step 3 we will find out the required modulus of section. What is the required modulus of section? That will be M by sigma BC or sigma BT, and in this case we know for beam having lateral support, we know sigma BC will become sigma BT, and that will be becoming 0.66 Fy. So, if I find out the value of sigma BC as 0.66 Fy is 250, then it will come 165, and maximum moment we have already calculated as 156.25 into 10 to the 6 Newton millimeter, right. So, from this equation we are going to get as the section modulus as 946,970 millimeter cube, or we can say 946.97 centimeter cube, 946.97 centimeter cube. So, with this we have to see what are the available section which we can use here. So, with the SP6 we can find that an ISMB 400 section will be relevant to use here. Okay. In case of ISMB 400, the section modulus is 1022.9 centimeter cube, which is little greater than the required Z required. Z required is 94697, right. So, we are providing the section, or we are choosing a section in such a way that the section modulus of the selected section will be little higher than the required section modulus. So, in this way we can find out the suitable section. Now, for that section, that ISMB 400, these are the relevant property which is required for calculating and checking other things. right. Like D, we know what is D, what is T in a I section. D is the overall depth, so that is given 400. Now T is the thickness of flange, right, and small t is the thickness of wave, that is given 8.9, and thickness of flange is given 16. Similarly, Ixx means moment of inertia about xx direction, that is given as 20458.4 centimeter to the 4, and this already we have told that the section modulus is 1022.9 centimeter cube, and H2 which will be required, the root from root to this distance, that is 32.8 millimeter, right. So, these are the required data which will be necessary for checking and calculating different parameters for final design, right. Now, what we will do? So, we are seeing that as we are providing section modulus little higher than the required. So, from bending moment of point of view, this will be okay. That means, the sigma c or sigma t, that will be less than sigma b c or t, sigma c or t, right. So, that we can assure, because z required is less than z required is less than z provided is more. So, definitely this will become. Next, what we will do? Next, we will check for shear. Now, the average stress can be find out from this expression, that is V by d into T, where maximum shear develops at the support, which has been calculated as 125 kilonewton, and this we are changing to Newton by multiplying 10 cube. So, V by dt means 125 into 10 cube Newton by d is 400 and T is 8.9. So, we can find out the value as 35.11 Newton per millimeter square, right. So, average shear stress is coming 35.11 Newton per millimeter square, which will be less than 0.4 Fy, right. It should be less than 0.4 Fy. Now, what is 0.4 Fy value? 0.4 Fy means 0.4 into 250, and this is coming 100 Newton per millimeter square. So, this is becoming less than 0.4 Fy. The average shear stress developed as 35.11 Newton per millimeter square, and the allowable shear stress is 100 Newton per millimeter square. So, it is quite safe. So, the section is safe from shear force point of view. Next, what we will do? Next, we will check for deflection. First, we will find out what is the allowable deflection as per the Coral provisions. Allowable deflection is, we know, span by 325. Now, span is 5 meter. So, 5 into 10 cube millimeter and 325 the coefficient. So, if we divide span by 325, we will get 15.38 millimeter. This is the allowable deflection for this case. Now, what is the deflection actually developing? That will be developing as 5 by 384 into WL to the 4 by EI, because we know this beam is supported by, means simply supported and carrying a UDL load, right. So, for this case we know the coefficient is 5 by 384, right. So, if we put those values like 5 by 384 into W is 50 and this is L is 5 meter, that means 5 into 10 cube millimeter, and then E is 2 into 10 to the 5 Newton per millimeter square, and this is millimeter cube, that section modulus 20458.4 into 10 to the 4 millimeter cube, and this is all are we are changing to Newton and millimeter to keep in same unit. So, W UDL load was 50 kilonewton per meter. So, that has to change to Newton per millimeter. So, 50 into 10 cube Newton by meter, meter means 10 cube millimeter. So, Newton per millimeter. So, that is finally coming, right. So, that is what we have put 50 Newton per millimeter. So, in this way we can find out the deflection which is coming due to the certain boundary conditions and the load which is coming 15.38 which is coming 9.94 millimeter. So, deflection with the load is coming 9.94 millimeter and allowable deflection is given 15.38 millimeter. So, calculated deflection or developed deflection is less than the allowable deflection. That means, from deflection point of view the chosen section is all right. From deflection point of view the chosen section is all right, because the allowable deflection is higher than the developed deflection. So, we can go for next step. Next step is what? Next step is check for crippling, whether the chosen sections are safe against crippling or not. What we will do in case of crippling? We know in this case, as this is a simply supported beam with an UDL, so there is no as there is no concentrated load. So, crippling only will happen at the support. Crippling only will happen at the support, because there is no concentrated load existing on the beam due to external load. Only as a reaction force the crippling will happen, right. So, for that we know the formula we have derived earlier, that is reaction by B plus H2 root 3 into T. Reaction means we know what is the reaction it is coming, right, which is 125 kilonewton. Okay. So, 125 kilonewton by B plus H2 into root 3 into T. B we are assuming the bearing length as say 100 mm, minimum bearing length. So, let us assume the bearing length as 100 mm. Then, and from the IS handbook, that is SP6, we can find out for ISMB 400 the H2 is 32.8 mm and root 3 into T. T is the thickness of the wave, which is given 8.9. So, if we calculate this value, we will get the sigma P value as 89.56 Newton per millimeter square. 89.56 Newton per millimeter square. Right. Now, as per the Codal provision, it has to be less than 0.75 Fy, and as Fy is, that means 0.75 Fy means 0.75 into Fy is 250, right. So, this is becoming 187.5. So, this is the allowable stress in bearing, and developed stress in bearing is 89. So, which is less than the allowable one, that means this is also safe, right. So, in this way we can check the assumed sections step by step and then finalize the section for a particular beam. So, next we will go for wave buckling. So far we have discussed about the design aspects of a beam which is laterally supported. Now, before going to start design aspects of laterally unsupported beam, let us discuss little about wave buckling. Why wave buckling happens? Because the type of section which we are going to use in case of steel structure, means in case of beam, is generally I section or channel section or T section like this, where the thickness of wave is much less than the width than the height of the wave, depth of the wave. Because if we see the I section, what we will see, this is a, say suppose this is an I section. Now, this is the depth of the wave and this is the thickness. Now, when a concentrated load coming into picture or a heavy load coming into picture, then what will happen? This portion may buckle, okay, which is called wave buckling. So, we have to take care this wave buckling effect also. When going for design of beam section using such rolled steel section, we have to check for wave buckling also, right. So, the wave in a rolled steel section behaves like a column when placed under concentrated load, because it behaves like a column, right. The wave is quite thin and is therefore subjected to buckling. Wave is quite thin and therefore subjected to buckling. The buckling of the column wave is influenced by the restraints provided for the flanges, right. The buckling of the column wave is influenced by the restraints provided by the for the flanges. Now, what are the type of wave buckling? Let us see. So, this is one case where the wave may buckle like this. So, this is case A, right. Another case is, say it may buckle something like this, right. This is B. Then another is, say first it will go, then start buckling. Another is, first it will start buckling, right. So, this is C and this is D. So, what happens and how we will calculate the effective depth of the buckling? Effective depth we have to calculate. What is the effective depth? So, what are the cases happening? That first we will assume that the bottom flange is restrained against lateral deflection and rotation in all the cases as shown in the figure. So, bottom flange is restrained against lateral deflection and rotation in all the cases. For the top flange, the end restraints and the effective depth of the wave to be considered are as follows. So, for top flange, for different cases the effective depth will be different. Like if it is restrained against lateral deflection and rotation, that means if the top flange is restrained against lateral deflection and rotation, then the effective depth can be written as d by 2. Effective depth can be written as d by 2. This is when this case is coming, right. Next, when restrained against lateral deflection and rotation, the top flange when it is restrained against lateral deflection and rotation, the effective depth will become 2d by 3, right. Again, when restrained against rotation but not against lateral deflection, we can find out effective depth as d, and when not restrained against rotation and lateral deflection, the effective depth is 2d. So, for various cases the effective depth has to be considered. In fact, this depth how to calculate, all these things are given in the codal provisions, right. Now, bearing stiffeners are required for this. Bearing stiffeners are necessary to provide to check the buckling of the wave, because to restrict the buckling of the wave we need to provide some bearing stiffeners. Now, as per code, bearing stiffeners should be provided where the concentrated loads or the reactions exceed the value of this sigma AC into T into B, sigma AC into T into B, where sigma AC is the allowable compressive stress in that section, T is the thickness and B is the width, right. So, sigma AC, this is the maximum permissible axial stress having a slenderness ratio of d root 3 by T. How it is coming, I will derive later, d root 3 by T, where T is the wave thickness and B, what is B? B is the length of the steep portion of the bearing plus the additional length given by dispersion at 45 degree to the level of the neutral axis. These things when I will derive will be clear. So, this is the plate. Now, if a concentrated load is say acting here, right, with P. Now, as per the assumptions, what will do? That will be dispersed at 45 degree angle, right. So, the value of V will become this one, B, right. So, this is B. Again, if at the support, what will be value of V at the support due to reaction. So, we are assuming that this also it is acting up to this. So, this will be the B. So, the magnitude of the B will differ for concentrated load at this section and for reaction, because at the support there is no scope to disperse the load in this portion, right. This is the neutral axis and this 45 degree angle it will disperse in 45 degree angle, right. Now, this is called H2, this is D and this is again H2, right. The section will be like this. If I section we are providing, so you can set the section will be like this, which is this is H2 and this is D, okay. This is bearing plate, this is also bearing plate, right. So, this is how it disperses the load. So, we can calculate the bearing length for buckling, bearing length for buckling can be calculated, right. Here H2 is what? H2 is depth at root of the fillet and D is the clear depth of wave between of fillet, right. So, we know H2, we know D for a particular section. So, what we will do? Now, we can find out the effective depth of the wave and effective length. First, we will find out effective length. So, effective wave, this will become, say if I say LE, this will become D by 2 in case when if flanges are against lateral displacement and rotation, right. So, slenderness ratio lambda will become L by R, LE by RY. So, this will become LE means D by 2 and Ry is Iyy by A, we can write. So, d by 2 by Iy will become in this case 1 by 12 b t cube, right, and A will be b into t for this wave. So, if we calculate this value, what will happen? This will become finally that d by 2 into 2 by 2, it will come 1 by 3, right, and t square. So, this will become, so 1 by root 3 means root 3 d by t. So, this is becoming basically d by t into root 3. Okay. So, slenderness ratio is lambda will become d by t root 3. Okay. So, why we are going to calculate the sigma AC value for d root 3 by t, I think now it is clear. The sigma AC, which is the maximum permissible value, because we have to see what is the slenderness ratio of that section, because the section is acting as a compression member. So, as a column member you can say. So, as a column member when we are going to consider, or compression member when we are going to consider, we have to find out the allowable compressive load on the basis of type of steel and slenderness ratio. So, slenderness ratio we have to find out across the depth, right, and then we can find out the allowable compressive load. The moment we can find out the allowable compressive load, then we can find out the allowable load, which can be taken care by the section itself. Now, another type of buckling we will discuss, which is called diagonal buckling, right. Diagonal buckling of the wave is not in general serious in rolled beam sections, right. In case of rolled beam section, generally we do not design against diagonal buckling, because it will automatically satisfy. Why I am telling? The possibility of diagonal buckling of the wave occurs when the ratio d by t becomes greater than 85. That means, the ratio d by t greater than 85, right, where d is the distance between the flanges and t is the wave thickness. D is the distance between the flanges and t is the wave thickness. So, if it is becoming more than 85 d by t ratio, then only this diagonal buckling may occur, right. So, all, but in practice what we see, that all rail sections have this ratio less than 70. For all rolled steel section, the ratio of d by t generally become less than 70. That is why we do not need to check against diagonal buckling, but when we will be going for design of a beam using built up section, in that case chances of occurrence will be there. So, in that case we must check for diagonal buckling. Now, let us see how diagonal buckling happens. Say a plate is here, right, say I section plate. Now, if this is neutral axis depth and if this is the section, right. Okay, now this is D, okay, and what is D1? This distance is called D1, that means this one, this is called D1, and this will act as a diagonal compression, diagonal compression, right. Now it will be something like this, right. Now the things may develop in this way diagonally, right, and this will be D. Okay. So, diagonal buckling can happen in this way and it will be in 45-degree angle. The maximum diagonal compression occurs at the neutral axis and will incline at 45-degree to it. Due to horizontal compression and tension below the neutral axis, the diagonal compression does not remain inclined at 45-degree at each point in the wave except at the neutral axis, but for a simple solution it is assumed to be inclined at 45-degree at each point. So, while calculating this, we will assume that the inclination is 45-degree at each point. This the thing which we will consider, right. Now, we will go through one example to see how we can check the buckling effect, right. The example is, say we are using ISW 600. This section we are going to use ISW 600 at 145.1 kg per meter and reaction is 185 kilonewton. Reaction at the end of beam is 185 kilonewton, right, and section is ISW 600. Now, check for wave buckling if the length of bearing plate at the support is taken as 130 mm. Right. So, bearing length has been taken as 130 mm. Now, design bearing plate assuming that the bearing plate is set in a masonry wall. Okay. It has been set in masonry wall and use Fy as 250. So, these are the data which has been given. So, what we will do in case of masonry, the bearing stress, allowable bearing stress can be considered as 5.5 Newton per millimeter square, and as we know the end reaction is 185 kilonewton and bearing 130 millimeter, and for steel table means for ISW 600 from steel table we can find out the thickness of the wave as 11.8 millimeter. These are the things which are given for the section. Now, this also is given at the code, that is distance between root of fillet and flange, that is H2 46.05, and depth of beam between roots of fillet H1 is given as 507.9 millimeter, right. Now, we will go for check of wave buckling, right. So, we know first reaction should not exceed this value sigma AC into TW into B, right, and so we have to calculate what is the limiting reaction, right, sigma AC into TW into B. Now, to find out TW is given, B is given, B can be find out. Now, to find out sigma AC we have to know the slenderness ratio. Slenderness ratio is H1 by TW into root 3, which we have calculated earlier, we have derived and we have seen, right. If we put this value, we will get the slenderness ratio as 74.55, right, because H1 is 507.9 and TW is 11.8. Now, the Fy value we know 250. So, from table 5.1 of IS 800 1984 corresponding to Fy and slenderness ratio, we can find out the value sigma AC, which is coming 106.5 Newton per millimeter square, right. We can find out from table 5.1 the value of sigma AC. Then what we will do? We can find out the length of stiff portion of bearing. So, that will become B plus D by 2, because this is 45-degree angle dispersion, this is B, right. If this is the bearing plate, then with 45-degree angle dispersion it will be, so B plus D by 2, and at the support only, so in this position it will not be, here only it will be, right. So, this is B, and as this is D, so sorry D by 2, so this will be D by 2 because of 45 degree angle. So, B plus D by 2, and B is given 130 and D is given 600. So, B we can find out 430 mm. Now, allowable reaction can we find out? Allowable reaction sigma AC into T into B. So, if we put the value sigma AC as 106.5, T as 11.8 and B as calculated 430, and dividing by 1000 to make it kilonewton, it is coming 540.4 kilonewton, and our end reaction is 185 kilonewton, which was given, right. So, allowable reaction is 540.4 kilonewton and end reaction is 185 kilonewton. So, the means design is safe, whatever section we have given, that is safe against the buckling. Now, what else we will do? We will design the bearing plate. For designing bearing plate, we know the end reaction is given 185 and the bearing stress in masonry has been assumed as 5.5. So, bearing area will be required as R by sigma. So, R is reaction force 185 kilonewton and the stress 5.5 bearing stress, allowable bearing stress. So, this is the area is required. Now, length of bearing provided is 130 mm. We have provided length of bearing 130 mm. So, now we can find out width. So, width will be the total area by 130. So, this is coming 258. So, we can use 260, right. Okay. Now, the dispersion of reaction occurs uniformly at 30 degree with the horizontal. So, we can find out this B value, which will be TW plus 2H1 cot 30. The value of TW is 11.8 plus 2 into H1 is 46.05 cot 30. So, if we put those value, we can find out the value B as 171.5 millimeter, and the maximum bending moment occurs, which will be at the center, which will become M is equal to R by 8 into B minus B, R by 8 into B minus B. So, if we put those value, R is 185, B is 260, which has been calculated. So, if we put those value, R by B into 8 into B minus B, we will get 2046.56 kilonewton millimeter, and the moment of resistance of the plate is can be calculated, that is sigma AC into Z. So, that value if we put, we will get this means, and then we can equal with this. So, MR will be equal to M. So, from this I can find out the thickness of the plate. So, thickness of the plate is coming 15.87, that means we can use 16 mm, right. So, how we are going to find out thickness? That making M is equal to MR. From this two equation we can find out the value of T. So, T we are finding as 16. So, all the values we found. So, we can say that provide the base plate as 130 mm by 260 mm by 16 mm. These are the value which we get. So, in this way we can find out a suitable plate dimension, right. So, with this today's lecture I like to conclude, and tomorrow we will discuss about the design aspects of unsupported beam. Thank you very much.